Hi everyone, welcome to Orgo Essentials, not your basic organic chemistry tutorial, episode 12. In this episode, we'll cover some miscellaneous organic chemistry nomenclature topics, including branched alkyl groups, some more challenging functional groups, and cyclic compounds. Let's get started. So there's one more nomenclature topic that can be found in simple acyclic compounds that we're going to cover, branched alkyl groups and how they're named. To understand this, however, we have to learn about degrees of alkyl substitution. This is a term that refers to how many alkyl groups and how many hydrogen atoms are attached to a given carbon atom. A primary carbon is one with only one alkyl group attached and two hydrogen atoms. In other words, it's bonded only to one other carbon atom. Here is the general formula for such a carbon, and here's an example with a methyl group attached. If there's just one alkyl group, you don't generally have to worry about adding prefixes. However, you may see the letter N to show this structure. Here is an N-butyl group. A secondary carbon is one with two alkyl groups and one hydrogen atom. It's attached to two other carbon atoms. Here is the general formula. Note that the second alkyl group can be here, here, or here. It doesn't matter which. Here is that formula with a methyl group and a propyl group attached. When a carbon is secondary, you may see the prefix sec. For example, this is a sec-butyl group. Compare this to the structure of that of N-butyl. Instead of all the carbons being in a straight line, like in N-butyl, they form one 90-degree angle. The carbons go in two different directions. Finally, a tertiary carbon is one with three alkyl groups, like this. In this image, there are two methyl groups and an ethyl group attached to that tertiary carbon. The prefix tert can be used with this structure, as in tert-butyl. Here, the carbons go in three different directions. Let's look at one example of these prefixes in action. Let's try and draw 5-tert-butyl heptane. First, we know that there will be 7 carbons connected to each other, because of the heptane. Next, we know that, on the 5th carbon, there's a tert-butyl group. We can attach that right on, like this. Done! In previous videos, we've learned about how to name compounds with functional groups, but we skipped a few: ethers, amides, and esters. First, ethers. You may remember that ethers are characterized by two alkyl groups with just hydrogen and carbon atoms, on opposite sides of an oxygen atom. This functional group does not have an IUPAC prefix. There are two different ways to name an ether. First, you may describe the molecule by the names of the two alkyl groups, separated by a space plus the word ether. For example, this molecule can be ethyl, showing this side, methyl, showing this group, ether. The other way is by deeming the shorter alkyl group an alkoxy substituent, meaning it's a substituent attached to oxygen. In that way, the shorter methyl group would be described as methoxy, and the ethyl group would be turned into the root name, ethane. This molecule would be methoxyethane. Another example of an ether is CH3CH2OCH2CH3. This molecule would be diethyl ether, because there are two ethyl groups on either side of the oxygen atom. You may also see this molecule simply called ether. Now, let's look at amides. Recall that amides are characterized by a carboxamide group, with the formula RC double bond O NH2. Before we go into the nomenclature of these groups, it's first necessary to categorize them a little further. Primary amides are those where the nitrogen atom is attached to just one carbon atom. Secondary amides occur when the nitrogen is attached to two carbon atoms, and tertiary amides are when the nitrogen is attached to, you guessed it, 3 carbons. Here's a molecule with all 3 different types. As you can see, These different groups just refer to where the nitrogen atom is in the organic molecule. Now that we've learned all of this, let's go on to the nomenclature part of amides. For primary amides, go along the naming process just like you're naming a carboxylic acid. After all, amides are carboxylic acid derivatives. At the end, change the oic acid to amide. There's no need to do anything else because it's implied that the amide is on the 1 position. It's at the end of the molecule. For example, let's try to name this compound: CH3, CH2, 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 CONH2. First, we can see that the amide is at the end of the molecule, so it's primary. Next, there are 6 carbon atoms, so this is a hexane of some sort. If this were just a carboxylic acid, we would call it hexanoic acid. Let's replace that oic acid with amide. Hexanamide. Perfect! Next, secondary amides. These are named exactly like primary amides, until the very last step. Once you have the root name and the other substituents, you're going to add the name of the alkyl group attached to the nitrogen atom to the substituent section of the name. You don't need to give it a number, just write the letter N. For example, this molecule is N-methylpropanamide. The propane part shows this section, the amide shows this section, and the N-methyl refers to this. Lastly, we have tertiary amides. Naming tertiary amides is just like naming secondary amides, except there will be 2 substituent groups with N as a position number. Let's look at this molecule. First, we can tell it will be a propanamide because there are 3 carbon atoms before that nitrogen. Next, we can see 2 methyl groups, so we'll have dimethyl as the substituents. These substituents are both attached to the nitrogen atom, so the position numbers will be N, N. Let's put it all together. N,N-dimethylpropanamide. Finally, let's learn how to name esters. Remember that esters are another carboxylic acid derivative, with the OH of carboxylic acids being replaced with an oxygen atom and an alkyl group. To name an ester, you're going to name the chain of carbons attached to the double-bonded oxygen atom. This group gets the suffix -08. Now, name the alkyl group attached to the single-bonded oxygen atom. This group is named like a substituent, but with no number. For example, this molecule is methylethanoate. That methyl is attached to the single-bonded oxygen atom, and the ethane is attached to the other oxygen. One more example. Let's try to name this molecule. First, that section attached to the double-bonded oxygen has 3 carbon atoms, so it's going to be propanoate. Next, the other side of the double bond has 2 carbon atoms, so it will be ethyl. Ethyl propanoate. Nice job! As you may be aware, not every organic compound is a chain. In fact, carbon atoms are known for forming cyclic compounds. These compounds have some distinct nomenclature rules, building off the steps we already know. First off, cyclic compounds are fairly easy to recognize. They're cyclic, forming a ring. Any organic compound with more than 2 atoms can be cyclic. However, the most common cyclic compounds you'll see in organic chemistry are cyclopentanes with 5 points and cyclohexanes with 6 points, as these are more stable than, say, cyclopropane. The names of cyclic compounds are also easy to recognize. They always have the prefix cyclo, no matter the substituent prefixes or functional groups. Otherwise, nomenclature is fairly similar to acyclic compounds. Cyclic compounds with just single bonds are called cycloalkanes, just like how acyclic compounds with only single bonds are alkanes. For substituted cycloalkanes with substituents attached, the root name is the name of the cycloalkane, with the substituent named with a prefix. For example, this is cyclopentane, and this is methylcyclopentane. If there are 2 or more substituents, then the carbons in the ring are numbered to give the lowest numbers, just like in the molecules we've covered before. One small difference. The 1 position always goes on one of the carbons with a substituent. Once you've numbered each substituent, you can list them in alphabetical order in the name. Finally, if there is a molecule where the acyclic part of the compound has more carbon atoms than the cyclic part, you could name the compound like the ring is a substituent. This can also apply when the acyclic section contains an important functional group. All of these new rules may seem confusing, but don't worry. We'll do one practice problem, then there are plenty of other practice problems available down below. Don't forget, you already mastered normal organic nomenclature. There's nothing you can't do. Let's try to draw 1-ethyl-2-methyl-cyclobutane. First, we know that this is cyclic because of the prefix cyclo. Next, like usual, we look at the root name to figure out how many carbon atoms are in that main section of the molecule. In this case, there are 4, because of that but. Let's go ahead and draw cyclobutane, like this. Now, all we have to do is add the substituents. We can number the carbons in any order or direction, but I'll go ahead and number them like this. Now, we know that there is an ethyl on that 1 position, like so. Next, there's a methyl group on the 2nd carbon, like this. In some drawings, you may see the implied hydrogens, which fill out every carbon's octet, but they're not necessary to see what the molecule looks like. We finished! That's it for this video. Like usual, I've included a document with some difficult nomenclature practice problems, including cyclic compound practice, some of the new functional groups we've learned, and degrees of substituent problems. Remember, practice makes better. If you have any questions so far, feel free to email me or comment down below. The next video will be about the properties of alkanes. I'll see you then!